Okay, so let's start our school on quantum materials, this year school. It is, as I explained, it is combined now with the beginning of our project, which is within the program of Core of Excellence of BNB, funded by BNDF. And for us, for Kyiv Academic University, it is very important. It is example of that international collaboration, which we say how it is important for science and for our and for this research intensive education, which is important standard, our standard, which we are developing. And that within this research intensive education, it is important that international that students are involved in interesting topics, in interesting science, and this is, as you know, could be can't be realized now without collaboration, without international collaboration. How modern science works. It is my pleasure here to start this conference with our German colleagues, to whom I'm very grateful for support, during all the years, and especially during starting from the war. They hosted mainly our researchers, and it is very important. Previous program, which we call Ukratop, was appeared to be very successful in a sense that we have many results, many publications, and a number of students, not only our students, but also students from different universities. They passed through these scholarships, and I was glad to observe how it is important for their career, for their development, and that this rather short PhD scholarships that okay, we should control also in parallel. We should control microphones, but I can do it. Because of this, I actually wanted to ask Volodya to sit here and to speak from another location. Okay, so try to keep your microphone switched off, but switch it on when you're speaking. Okay, now actually the topic of this project, and the main topic of our research in the related laboratory and in the department of educational department of CAU. It is quantum materials. It is one of the most important topics, and this school is devoted to quantum materials. The first day today, we call it German Day, and it will be in English. And it will consist of presentation from our German colleagues. I think there's 3 presentations will be. Then we could actually all the school during all presentations we are open for questions, and we are glad for discussions. We will have special time if you have some questions, but we open for questions anytime. It is just in general. Actually, the second day tomorrow, it will consist of lectures. It will be Ukrainian day in a sense that the working language will be Ukrainian, and the program contains presentations, lectures, which are like short reviews on the topics, on the lecture courses which are taught in CAU and devoted to quantum materials. This is first part, and after lunch it will be a short demo demonstrations, like tours about experimental facilities in Dresden, and we planned in Ukraine. We will see how we could organize it if connection will allow. But I think we will start from German tours, right? Okay, so I stopped. I think I see the Bernd is ready. Therefore, it is my pleasure to invite to welcome Professor Bernd Buchner, who is director of IFW Dresden and who is the main responsible for this project. It was his initiative from very beginning, from Ukratop, and I welcome Bernd, please.
Okay. Thank you very much, Sasha. So I will try to share my screen now. So it's also, I should emphasize that this project, this new project, which we are now starting, does it work?
Yeah, it's working. If you make it on the full screen, it will be a bit better.
I'll do my very best. Let's do it like that. Okay. So that this project...
Now it's not full screen. It's just what you see on different monitor, probably. You can switch.
Let's do something like
presentation mode.
Now?
Now it's perfect. Yeah.
That's better. So, so that this project, let's go back. Oh, no, sorry. So this project, which we start now, it's also very, very important for us. And I think it's a continuation of a big success story. And thank you very much that you give me the opportunity to be the first speaker here. Actually, I was asked not to give a scientific talk, but to give an overview over the institute and over the project. And I'm I'm happy to do that. We'll discuss a little bit the scientific cooperation between Ukrainian scientists and us at the IFW Dresden. So introducing this German-Ukrainian Research Center for Quantum Materials. And here you see a picture from our entrance where some of the Ukrainian guests were presenting some flags from Ukraine some time ago. So this doesn't work. Why doesn't this work? Okay, let's do it like that. Let me first start with introducing our institute. So the name of our institute, so IFW Dresden, stands for Leibniz Institute for Solid State and Materials Research in Dresden, and we can go through this name. So what does it mean, Leibniz Institute? That means we are one of the institutes put together in the so-called Leibniz Association. Leibniz Association is an association of non-university institutes. Nearly 100 of these Leibniz institutes are present all over Germany. They are independent institutes. This is non-university institutes. They cover a very broad range of topics from social science, economy, but also natural science. And we are one of the only institutes, I would say, where physics or fundamental physics also plays a role. But in general, all these Leibniz institutes follow the agenda from theory to applications. So theoria cum praxi, that's, let's say, a general theme of all these Leibniz institutes. But the rest, we are rather independent and loosely connected in these Leibniz association. So what we are doing is we are doing solid state research. So we are doing fundamental science from theory, experiment, and synthesis on all kinds of condensed matters. But we also try to go a step further from these fundamentals to something which is called materials research. So where we really try to also get some technology development or some material science, not only condensed matter physics, but also material science in the sense of materials engineering is a part of our story. It's also in our name. Okay, and we are located in Dresden. This is a picture from Dresden. It's an old city, let's call it like that. There's a lot of Baroque in there, old churches, there's a Frauenkirche. So, but we also have a lot of high-tech meanwhile in Dresden. There are many companies, many research institutes, a large university, one of the excellence universities located here in Dresden. And that's also should emphasize, we have a really Ukrainian community now. This number is given by the city. So there are about 8,000 Ukrainian people here around. So let's see, if you come here, you can also speak Ukrainian. So what we are doing is, and that's our slogan, we are working on materials for technologies of tomorrow and beyond. And for us, it's quite important that, okay, on the one hand, it's clear we are working on materials. That's the common theme of our research at the IFW. We have technologies in our mind, but it's important for us to state that this is not technologies of today, but also of tomorrow and beyond. That means we are also trying to explore really new concepts for technologies, materials which are promising for future technologies, which are not even cannot even be foreseen at the moment. And this materials-oriented research and development we do in 5 disciplines, from theoretical condensed matter physics, experimental condensed matter physics, chemistry, materials engineering. So this is now these 2 engineering parts, where we have materials science and materials engineering and electrical engineering, both disciplines. And here are just some examples showing you the broad spectrum from skyrmions, which are also very much relevant for QMatS. This we will learn more on platinum bismuth later on. So it's a superconductor and topological material, but also some steel is studied here. Thermoelectric coolers or solar cells, all this whole range relevant for condensed matter of material science. So again, we are organized so we have 5 disciplines, and we are organized in 5 so-called IFW institutes with directors. These directors are jointly appointed at the university. So we always have both this non-university character in the IFW, but simultaneously the professors are at the university, which is very much relevant, for example, for all kinds of teaching activities, for PhD thesis, for supervising master students. This can also be done directly with the university, since the directors are simultaneously full professors at the university. So I myself, I stand for the Institute for Solid State Research. I'm located at the Faculty of Physics, and we are working on experimental condensed matter physics in our institute mainly. Cornelius Niersch, the second director, is working in the Institute for Metallic Materials. He's associated with the Faculty of Engineering, Materials Engineering. Our new colleague, Anjana Devi, she's working on materials chemistry, connected to the chemical Faculty for Chemistry in Dresden. Jana is also a rather recent professor, Jana Weinshoff. She's associated with the Faculty of Electrical Engineering. And last but not least, Jeroen, who will give the next talk, and he's also associated with the Faculty of Physics, but he's working on theoretical condensed matter physics. And then we have 2 W2 professors, also both. There's Axel Lupp, working on TEM techniques, again, also Faculty of Physics, and Julia Hufenbach, she's professor at the other university, nearby university, which is very strong in these materials, metallic materials or materials engineering, and there she's a professor. Okay, this is our team of the directors and professors. The resources of the institute, we have about 500 or 560 people working here, 250 scientists. Out of these 560, we have a lot of PhD students. You see, teaching is a large activity, so we have 140 PhD candidates, including visitors, but we have also master students and bachelor students working here in the institute. So the total budget is about 47 million euro at the moment. So it's about the largest part comes directly from the federal and state governments. One has to emphasize that this is not only money which you can use for research. So for example, we have the buildings and we have all this administration and all these things, you have to cover that. So this is the total money. These 12 million is the money which you get from project grants, either from European Union or from DFG, so from German Research Association, and also from the BMBF, where also our joint project is funded. So this is the budget and the infrastructure. So we have about 30,000 square meters lab and office space. We are directly located at the university, which is a big advantage. So that means we can do lectures here, and also for students, they can really join the lectures at the university. There's a very strong contact to the faculties. And we are, on the other hand, rather well equipped with all kind of infrastructure which you need for materials research, starting from crystal growth and thin film growth, clean room, we have a large clean room, and then we have a lot of spectroscopy and methods to characterize the materials. Our research, we are studying phenomena and functions that occur at the level of electrons, atoms, and molecules, or nanostructure. And what we want to do is we want to understand the materials, want to calculate or even predict the properties of materials. So this basic research is a part of our study. It's, of course, connected to theoretical physics. We are developing methods to understand the materials. We do not only use methods, but we also develop methods to understand materials. And then finally, we also ask ourselves whether we can modify, we can optimize the materials to induce new functionalities or even applications. And we have this triangle here discussing our main aspects, and you see these quantum materials, which is of course also important for our joint activity, is mentioned here. We also do that on nanoscale materials, and we have in mind the function and maybe also sustainability of these materials. A little bit more detail, we have this research area, and these are these functional quantum materials. So we try to get new functions due to novel, unconventional electronic properties. So superconductivity, magnetism are the prime examples. Topology also is maybe a new or more modern aspect which fits to this whole activities. And then we have activity which is more located on nanoscale objects, where the function comes through size, so that the properties and functions result from really structural arrangements or nanoscale aspects which are then relevant. We combine nano and function in this research area 3, where we address quantum effects at the nanoscale. Of course, if you want to go to apply quantum materials, you typically have to have some devices. You have to have this nanoscale aspect as well. And then we have a research area 4, which is more towards applications, where we really try to improve, for example, photovoltaic technologies, sustainable electronics, and similar things. So these are the research areas. And in the next minutes, I will show you some highlights from recent work. And the first one is this work on platinum bismuth 2, which will be later discussed in more detail. That's a beautiful, nice example because it's an interaction between these disciplines. So crystals of platinum bismuth as a two-dimensional material are synthesized here in the institute. They are experimentally studied in detail, for example, by photoemission, as you will later on show spectacular properties. And there's a close connection to theory, where the theoretical calculations or even predictions are made. So theory, chemistry, and experimental physics come together and try to do nice joint work. Actually, this nice work has been published in Nature recently, but it's not only a nice example of the joint activities within the IFW, bridging these 5 disciplines which we have. It's also a nice example for interaction between Ukrainian scientists and Germany, since our first author is Andrei. He was an UCA top student here and is now close to finalizing his PhD work. And then there are 2 other guys which have Ukrainian background, let's call it like that. And we are also participating in this work. This is an activity which was basically driven by the experimental physics. So the idea of having really new properties like the superconductivity in topological material. This is another example. And here the idea came from theory. And it's also very recent work. It's also related to Ukrainian PhD student here. It's the first demonstration of a non-emission topology in a condensed matter system. And that's, you see this multi-terminal thing. And what you measure here is a transport property. And what you mimic with this device is really an Hamiltonian, which has been derived in the theory. So it's, let's say, an experimental realization of a non-emission Hamilton operator, Hamiltonian. So, and then you can really study this thing. You can compare to theory, but what you can also do, you can go a step further. You can really drive this to applications, and there is a patent application is pending, and there are a lot of activities now going in this direction. And QL is really very important in this activity as well. I'll give you some other example. This is also a rather recent activity, and this is you see in material, interesting material is a layered material. It's also an intrinsic van der Waals material, but in this case, a complicated one. But what you see here is on the one hand, it contains manganese. That means a material which has spins, and so you have layers here which are magnetically ordered, actually ferromagnetically ordered. And then in between, you have layers of bismuth telluride. Bismuth telluride is known as one of the famous examples of a topological material. And so you have a connection between magnetism and topology. And this is very promising. There are clear predictions that there should be surface states which are protected, which can be used for spin transport. And okay, this work has been attracted a lot of attention. Here in this case, it was initiated by chemistry, I would say. So chemists, we were able to grow this for the first time. That was Anna Isayeva at that time. Then there was a big team with experimental theoreticians again. And then there was a lot of following works studying this material. Another example, also closely connected to activities which might be relevant for our consortium. This is now from Nicola Poczer's team, from Cornelius Niel's team. What he's working on are some heterostructures which are formed by twisting superconductors. And the starting material is this bisco. This is one of the cuprates, where again we have this van der Waals bonding in the bismuth layers. You can exfoliate it and can twist it and put it on top of each other again. And you end up with some Josephson junctions, which then, of course, the properties of these Josephson junctions depend crucially on this twist angle. And this is, let's say, also an ongoing activity for both studying the basic properties of such Josephson junctions, but also there are ideas to generate some kind of functionality, some kind of devices in this direction. Next example is again van der Waals material, which is often studied here. These are, you see again, these 2D materials. In this case, these are materials which contain iron and nickel. So they are again magnets, and they are 2D materials. And what has been done in these two papers was the study of their electronic properties, trying to understand their general characteristics, whether it's a Mott insulator, or what is the origin of the magnetism here. And of course, again, the idea is then to exfoliate these materials, to go down to monolayers, to manipulate the magnetism, to connect these magnetic 2D materials, 2D materials to superconducting or topological things. So this is just the idea using this van der Waals text to do devices and physics. Sorry, I continue. That's another example, very much relevant for work in our consortium. This is now work based on our TEM expertise. This Axel Luppes is crucial here at that point. And what they studied here is really the magnetic profiles in such curved nanostructures. And I think it's correct to say that we have perfect methods, TEM-based methods to study really the 3D magnetic textures in all kind of materials. You can measure 3D texture of fermions, and you can investigate them in very much detail. Another example from 2D materials. In this case, it's again chemistry driven. You see the new material here, where you have this typical motif of 2D materials, but here the top and the bottom layer are different, and therefore these materials are called Janus materials, have been grown here in Silke Hampel's team, published in a chemistry journal, and now the physicists start to investigate this material, look whether there are really interesting new properties originating from this fact that we have, let's say, a different version of a 2D material. Okay, this is already mentioned earlier, perovskites, solar cells, as Jana Weinshoff mainly working on there. She's very active, very successful, very visible in optimizing the performance of these new materials, these new photovoltaic materials. First demonstration of solar cells based on formation of phase heterojunction was the main topic of this recent paper. Okay. So there were a lot of examples of recent work. So we have a lot of ongoing research activities. We have these research fields based on quantum systems and based on nanoscale materials. But we also have a lot of, I would say, unique high-end methods. And this is just one example. Also, we developed these methods, the so-called high-resolution yields machinery. So it's TEM-based, so it's connected to Axel Lupp. Axel is professorship is paid by a company, so this is a company which really is dealing with optimizing some such objects like the monochromators or filters here, and together with the company we are developing this spectrometer. It's at the end of the day looks like a usual electron microscope, but in situ there are monochromators. There's a special sample space which allows cooling down to helium temperature. And there's an energy filter which allows to measure with extremely high resolution the energy of the electrons. And what you can do that, having a monochromatized electrons and having a nice energy filter here, you can measure the energy loss of electrons when they pass the sample to the sample. And this means you can do spectroscopy. You can do spectroscopy of excitons, plasmons, and all kind of other excitations. And this you can do now spatially resolved, so with sub-nanometer resolution in principle. Maybe not for the highest resolution, energy resolution, but of course, you have TEMS, we have sub-nanometer resolution, spatial resolution, and you have a momentum resolution. So you can also measure the excitations as a function of Q. And that's something unique. If you combine this together with the low temperature, then it's a unique method which is currently developed here at the IFW. And the first experiments are running now, first papers appear, and we are still improving the energy resolution. There's another example far away from this basic science. This is really applied science, the surface acoustic waves. So we have two groups actually working on such applications based on acoustic waves like this, which can be controlled by electrical fields. And of course, in piezo materials, you can do that. Using this technique, you can create sensors, you can create telecommunication components. So most of our modern handies actually use patterns which have been derived together with industry here at the IFW for filtering frequencies. At the moment, we are mainly focusing really on sensors, for example, for wind turbines, get information on the ice formation or even clean the wind turbines from ice if necessary. We can do high temperature sensors. So there's a lot of activity ongoing in applications, and this is connected in this SAW lab Saxony. That brings me to these patterns. So we have a lot of publications. You saw all these Nature articles, which I've shown you earlier, but we also have a lot of patents here in many different directions. So at the moment, it's about 67 patents we have in Germany, also international patents. So roughly, we have about 5 to 10 patents applications every year. And these patents are important also for industrial corporations. So for example, we have the licensing of the DFT code, the FPLO, which got theory code, which is licensed. But it's also, of course, connected to spin-offs. So we are at the moment preparing a spin-off, but there's also recent spin-off, and I would emphasize this fermiologics. This is connected to ARPAS, the new principle of a detector, which has been that was the idea of Sergei Borisenko, as mentioned here. He has then developed, wrote this patent and developed this prototype back in 2018, 2019. There was also some support coming directly from IFW and also from funding organizations. And then now, 4 years ago, he founds a startup company, this fermiologics, this new detector, which allows to Fermi surface mapping. I don't know whether Sergei will describe in more detail about that, but at least this machine is also crucial for our joint activity. And that's a very nice example that you really come from fundamental science, from fundamental spectroscopy to even to spin-off companies. So fundamental science, nice publications. applications. We have a lot of international corporations also. And this is a list of cooperation partners which I usually show. You see several of them are in Italy. We have close cooperation people in India as well, and in Calcutta, Amsterdam, in Grenoble, also in France. We are setting up something very close with Czech at the moment, nearby. But a very, very important aspect here is also our joint activity with Ukraine, which I will describe in more detail in the next minutes. Maybe I should also mention that the IFW is the best ranked Leibniz Institute in the Humboldt ranking. So that means a lot of foreigners come here and get funding then from the Humboldt Foundation to stay here for 1 or 2 years and then go back to their country typically. And then the Humboldt Foundation even gives a chance that then postdocs from Germany can come to the place where the former Humboldt fellow is now working. So we have a lot of successful applications in this Humboldt Foundation. We have Humboldt prizes, fellowships, partnerships. Also, we have also Humboldt partnership. Actually, with Kyiv, we have a Humboldt partnership is also ongoing. So then when we have a look on the ongoing cooperation with Ukraine at the moment, so we have several projects, and they also cover a broad range of activities. You see, we also have nice activities on machine learning for additive manufacturing, which brings together, let's say, theoretical physics or computer physics, let's call it like that, and this really very applied material science. Okay, this doesn't work. Sorry, I'm trying to. Yeah, okay, good. Links together theory and theory and material science. We have since various years an institute's partnership where we work on van der Waals materials. You saw how relevant this is, and we study emergent superconductivity in van der Waals semimetals. That's with Kyiv. At the moment, we have 5 fellows paid by the Philipp Schwarz Initiative for scientists at risk. So there's still a chance to get particular funding for Ukrainians here in Germany. We have ongoing funding from the European Union, also a fellow for Ukrainian scientists from TU Dresden. We have a fellow, and there are also a lot of Ukrainian people now integrated in DFG research projects. Actually, there is a chance to get funding from the DFG to pay people in the Ukraine. We are currently waiting for the result of such proposals, which we have submitted. But there's already ongoing research in this direction. I should also emphasize the success story. Sasha already mentioned this UKATOP project. It was funded between 2018 and 2023. So that was dealing with topological order of electrons. That was the interaction of these 3 institutions. So IFW together with TU Dresden here, and then these 2 institutions in Kyiv. You can also have a look on the homepage. I think there are a lot of giant people. That was really, for us, it was really a big success story. Great thing. Now let's move on to this, to the topic of this new project. So German-Ukrainian Research Center for Quantum Materials. What we are doing there is, again, research, education, and innovation. We have a QMatS team here in Dresden, and we have a Leibniz lab in Kyiv. Project start is just last month, so June 24th. It's for 4 years, and there's a substantial funding. So if you compare the numbers in the beginning, so we have about 10 million per year. So here it's whatever, 600,000, 700,000 euros. So it's a really substantial amount of funding also for us. It's a very important project also concerning funding. It gives us a lot of options to do something. Let's start with the joint Leibniz lab in Kyiv, which we want to set up. We want to improve. The director is Sasha Kortyuk. There are 3 postdocs, 6 PhDs. All of them will have, hopefully, the chance to have research stays at the IFW funded by the project. We also try to develop scientific infrastructure in Kyiv directly. There are some examples of machines which have already been transferred to Kyiv. There's a crystal is a floating zone furnace, optical floating zone furnace, which allows traveling solvent flux melting, growth of oxides and other materials here. We have a magnetocryostat, which has been transferred. We will transfer soon a multi-target sputtering machine, a sputtering system, which will be transferred in the next weeks or months. And then within the project, we will set up a mini ARPAS where this detector, which has been developed by Sergei Borisenko and which is now sold by Fermiologics, will be a main aspect. And we hope to set up this mini ARPAS, and then it will be transferred hopefully next year. So this is the joint lab. The research is dealing then with novel quantum materials, optimization of materials, interfaces for potential applications, and quantum devices. You see, these words are very similar to that what you heard about our main activities as the IFW. So this is really research which is in the core of our interest. We will have this combined multidisciplinary approach, bringing together theory, synthesis, and experiment. So it's also very nicely fitting to IFW's activities. And then new aspects are this artificial intelligence assisted materials design. And this will rely to a large amount on these novel ultra-fast Fermi surface mapping. So this new detector, which will be then the main part of this new mini ARPAS system. So this research and education. So within this project, we will have also a chance to establish a sustainable research education system that helps to convert brain drain into brain circulation. That's our hope, that people really go from one side to the other and circulate, and that there will be a really nice exchange. So there will be an option for all students to come to us. There will be a student training at the Leibniz Lab in Kyiv. There will be a student exchange program, bringing students for some time to Dresden. For example, we will have 1 semester research stays at the IFW for master students. And what we also want to establish now are so-called binational doctorates, so that the PhD degree is valid at both places, in Kyiv and in Dresden. And this we did already with France. We established it also with universities in Italy, and I hope we can also be a substantial important part of our educational project part within QMatS. The innovation part is also important. So we want to promote the knowledge and technology transfer between the institutions and try to create an innovation network, including also innovation-oriented education, of course, but also try to foster activities towards spin-offs or startups or spin-offs. And of course, Fermiologics are mentioned here, but also this academic city, which is an aspect in Kyiv, which could be very important in this respect. So there are a lot of opportunities for young people here at the IFW. You can work in exciting current scientific topics with state-of-the-art facilities. You can come here for short research stays. You can apply for PhD, for binational PhDs. You can apply for scholarships with other facilities, with other organizations. So there will be strong support from our side, and everybody is welcome if you're interested to come here during this project. Or besides that, and if you want to learn more on our institute, you can look at our homepage, in particular on the IFF. This is the Institute on Condensed Matter Physics, where I'm responsible for. If you want to learn something about theory, then you can go to this homepage. And if you want to learn something about our joint project and the progress, you can go to this homepage, which will be available soon, now or later. So this is what I want to say. So thank you very much for your attention.
Thank you, Bernd, very much for a very informative talk and for very informative presentation. Please, questions. In Kyiv, no alarm, but I think I hope all the people are sitting in safe place. Who here you can go to shelter actually. If you go to shelter, people don't. So okay, but we do not have too many people. Okay, so questions, please.
Hi.
Alexei, yeah, please.
Hi, I have a question. Can I ask?
Yeah.
Please.
Yes. I hear you speak about oriented crystals. Can you please explain the technology of their growing? how orientation is directed by which influence of which?
Okay, so when we discuss our synthesis activities, we have a broad range of methods. So one aspect is this flux growth or also optical floating zone of large single crystals. In flux growth, at the end of the day, you follow a procedure, then you cool down the flux, and then you sort out to look for the crystals, and then you have, let's say, hope that crystals grow, and then you have to orient them later on by X-ray diffraction. In the case of this traveling solvent flux melting, so this floating zone thing, you sometimes start with a seed crystal, and then the orientation is given already a bit, but also there, it depends on the material, on the properties, how the materials grow and how single crystals grow. But there are other techniques. For example, if you look at all these van der Waals materials where you have these clear two-dimensional structures, they are often grown by so-called CVT or CVD, so chemical vapor transport or chemical vapor deposition techniques. And there you start from some kind of gas phase, and you have a transfer in the gas phase to a substrate, and then these materials grow on the substrate. And then let's say the challenge is to get either large crystals or you want to have ultra thin crystals. Sometimes we grow very thin, small crystals, which we then use for transport measurements, or we even grow heterostructures. So we start from one material, and then on top of that, we grow different materials. So this is CVD grown, or for 2D crystals. You can even go a step further. So our chemist colleague is working on so-called ALD. There, she's working with monolayers of materials, and then the chemical reaction takes place on the substrate. And this is very important for all kinds of applications. If you want to make devices, then you put in via the gas phase, you put in molecules on some kind of material, and then you make this chemical reaction to get a monolayer of a material. And this and Anjana, she's a real expert. She can do that with very different materials. Often it's not monocrystalline, but in best cases, even a single crystal. And then, of course, we have the other techniques, as MBE or PLD, where you grow thin films layer by layer in best case for MBE. So there's a broad spectrum of different things. If you need huge crystals for neutron scattering, you have to do it with this floating zone machines. If you need nanocrystals for transport, often CVD or CVT is the right thing to do.
May I ask?
Okay, sorry, my microphone was switched off. Please, Kirill, if you have questions, raise a hand or just switch on microphone and proceed.
Yeah, on the slide, you explained research by Joint Center QMatS. There's lens layer, but we in Ukraine have no facilities to produce 3D lenses. I'm now ordering if I need from Delft or other universities. So does Leibniz Institute Dresden, or TU Dresden has such facilities to produce custom lenses for these experiments?
This I don't know really. So on the QMatS research, I showed this detector with a lens, which has been developed by Sergey. Okay, this is the idea of Sergey, and this is now built up by the company Fisuma here at the IFW. No, Sergey, maybe you can help me at that point. In principle, we have, of course, a workshop here. We have electrical workshop here. We have mechanical workshop. We can do a lot. But this depends. I would say the answer to you depends on the question, what you would like to do. Yeah.
Were you interested in optical lenses or electronic lenses?
Optical. I'm head of photonics cluster.
Okay.
So it's electronic lens, yeah, not optical.
On the figure, that was an electronic lens. No.
Okay.
We are not, so in our research, optical lenses do not play a crucial role. Let's call it like that. I think that's fair to say. Yeah.
Okay, thank you. It's clear.
We buy them.
We buy them. We certainly buy them. And maybe if there is a concrete interest in having something, we should discuss this. And I don't know. I cannot promise this story, but typically one finds a way if it's necessary. If there are some special things we could do here, but we are not experts in optical lenses.
Thank you. It's clear. And second question, you mentioned artificial intelligent assistance research. And do you use quantum computing and quantum modeling for research of materials properties?
So this I transfer to Jeroen. So he's a theoretician and he can tell you what we are doing with artificial intelligence. I only have a natural intelligence, and even this is limited.
Yeah. Well, also that's the only thing I have, and it's also limited. But yeah, what we do with machine learning techniques is more or less standard approaches, and we apply them to typically high throughput. Well, there are different directions, but one of them is doing high throughput calculations on materials to either screen for materials with interesting properties or design materials with interesting properties. So we are working on quantum materials, so materials with quantum properties, but we're not using quantum computers to do machine learning, which is, in itself a very exciting and I would say mathematical or informatics topic, but that's not our not something we do. Another direction that Bernd mentioned is the control of very complex manufacturing processes. So, for instance, this additive manufacturing, where you, with a laser, melt a material or powder in a bed, and then in that way make 3D printing of metals, which is a very complicated process, which you want to kind of feedback in real time. So you're observing some quantities, and then you want to feedback in real time to adjust the process. And this also requires some very smart informatics solutions which are related to pattern recognition and machine learning. So these are just two examples of things that we are interested in and doing.
Thank you. Actually, we have in Lviv enterprise who made nano printing, nanoscale additive printing with different materials called Novi Nano. So
yeah,
okay, it's interesting. Okay,
but maybe that would be interesting really to team up in some way.
We have a project with Kyiv, with the Franchevich Institute, but that would be interesting. And I'll write you an email about it later.
Yeah, and maybe
I'll connect you.
Yeah, because there are other options to try to get some funding, some joint projects. So let's say the DFG, which I've mentioned, offers a possibility to transfer money from Germany to Ukraine. At least formally, it seems to be possible. We'll see how it works. So that means that could be a short notice way to get funding for such dedicated projects if there is a joint research interest. Yeah. Going beyond, okay, we can team up with our QMatS, but we can also do on top of that such individual small projects if you want.
Thank you.
Okay, thank you. I see that Alexei still have raised hand. Alexei, do you have a question?
I have additional questions. Do you have experience with orientation of liquid crystals by surfaces or etc.?
Oh man, I think we do not have real experience on that. Liquid crystals. So it's not a topic where we are good. So maybe I should not promise too much. No, I think let's say Axel is not here with the STEM guy, and he has a lot of things what he can do and a lot of ideas what he can do. And if someone could work in this direction, then Axel could try to look. Whether I don't know whether TEM is able to help at that point. I don't know, but we have no experience in this direction. No.
Okay, if there is no more questions, then thank you, Bernd, again for very nice presentation. And we switch to another case, and it is my pleasure to welcome Jeroen van den Brink, who is director of Theoretical Institute, as you could see, as you could saw. Actually, he will speak about a very hot topic now, which called altermagnets. So this, it is my pleasure to invite him. Please, to welcome. Yeah, it's perfect. No. No.
Okay. Thank you very much, Sasha. Yeah, so I'll talk about today. I'll talk about I did something. I have to share again. I'm sorry. I messed things up. You still seeing my screen?
No, I'm just see you.
Okay, I'm sorry.
Yeah,
okay.
Now I see a screen, but
there it is.
Yeah, now it's fine.
Okay, I'll talk about altermagnets, which is a relatively new topic, as there's not many people probably know what an altermagnet is. My goal of today is just I'm already happy if you get an idea that an altermagnet is something different from an antiferromagnet and a ferromagnet, and in which respect it's different. The research we're doing in Dresden is with a lot of people now, partially here at IFW. You see Vladimir Kravchuk and Kostya Yershov, for instance, but also people outside our institute, colleagues in Sweden, Kong Lee, Oskar Tjernberg. I'll show you some data from them. For instance, also Helen Gomanai in Mainz. Okay, it's a hot topic. There's a lot of things being done, and these are just from the last year. Just the problems we have been working on in altermagnets. We have been working on altermagnetic materials, altermagnetic spin textures, topological Weil altermagnetism in chromium and timonite, curvature-induced magnetization effects in altermagnetic films, fluctuation-induced piezomagnetism in altermagnets, and altermagnetic anomalous Hall effects. So just to give you impression, lots of things are going on. I will not speak about all of these. I give in the end 1 or 2 examples of the work that we did. But let's start with the basics and try to understand what an altermagnet is. And here, well, I hope we all know what a ferromagnet is, a local ferromagnet with local moments. I take a 2-dimensional lattice, and I have my spins that are vectors, if you want, that are coupled to each other. And the coupling is, if the coupling constant J is smaller than 0, then the vectors want to be parallel. And I get this ferromagnet on the lattice. And I can ask, what is the symmetry of the wave function? And you see here that the wave function is invariant for translation by 1 lattice spacing. It's obvious, right? So this means that if I have 1 spin pointing up, all the other spins will be pointing in the same direction, and that will generate for me a finite total magnetization. The symmetry, just this translation symmetry, implies a finite total magnetization of the system. Now, if I look at a band ferromagnet, where these electrons with a spin can move around, then I get a band structure. So I have to look in momentum space. An example is iron or nickel. And because of the atomic exchange interaction, the local atomic exchange interaction, there will be spin split bands. And for instance, the band with the majority spins, so say the spin up band, will be filled. This is momentum, this is energy. It will be filled until the Fermi level. And the spin minority band, say the spin down band, might also be occupied, but only partially occupied to a less extent. And this gives me, again, a total magnetization because of, in the end, this same symmetry, this same translation symmetry of the ferromagnet. And the splitting between this majority and minority band is the exchange splitting, referred to as exchange splitting. And this is typically in the order of can be in a 3D system like iron or nickel, it's, let's say, 1 electron volt or so. This is a large energy scale. These bands are pretty much split. Now let's go to a antiferromagnet. Antiferromagnet, local antiferromagnet. Again, I could write down this Heisenberg interaction, but now take the J, the exchange interaction, larger than 0, so that these vectors want to be antiparallel. And this results, for this nearest neighbor interaction, into a pattern where there is spin up, spin down, spin up, spin down. There are 2 sublattices. An example of such a spin ordering in 2 dimensions or quasi 2 dimensions is lanthanum 2 copper 4, the material that's related to the high TC superconductors. So what is now the symmetry? Well, the wave function now is invariant for translation by lattice spacing again. But if I do this translation by the lattice spacing, also I have to flip the spin. So this is done by time reversal. Right? So the symmetry of the system is now translation times time reversal, giving me, as a consequence, a total 0 magnetization. And this means that there's a Kramers degeneracy at each momentum, that each momentum, any states will be twofold degenerate. How does this look if I now go to an itinerant picture, so the band picture? If I have a band antiferromagnet, and I took as an example here for you barium, iron 2, arsenic 2, which is again the, say, mother compound of a superconductor, in this case the iron-based superconductors. But when it's not when it's pristine like this, not doped, it's an antiferromagnet, and it has bands. But now also these bands are twofold degenerate. So I have at each momentum a band has of spin projection up and spin projection down. This is this Kramers degeneracy of the bands at each momentum. This is true as long as the system doesn't have spin-orbit coupling. If I introduce spin-orbit coupling, then these degenerate bands, in general, they will split up somewhat. But the spin-orbit coupling is typically much smaller than the exchange interaction, the local exchange interaction. For iron, the spin-orbit coupling is in the order of, let's say, 10 or 100 milli-electron volts, so 1 or 2 orders of magnitude smaller than the exchange splitting. If you go to F systems, for F system, then of course this is different, but for the 3D, 4D systems, this is normally the case, that the spin-orbit coupling is a smaller correction to the magnetic band structure. Okay, now let's look at something that's an older magnet, and the example I give you is a checkerboard antiferromagnet. So this model is well known. I have an antiferromagnetic interaction on the nearest neighbors, which I have in brown, but I add a ferromagnetic interaction along the diagonals. And this is such that only on every second square, I have this next neighbor ferromagnetic interaction. That makes it a checkerboard, right? And I can ask myself now, what is the magnetic ground state of a system with these interactions? And the answer is not very difficult. It's again the antiferromagnet, because in the antiferromagnet, my neighbors are antiparallel, and the next neighbors along the diagonals, they are parallel, but I have a ferromagnetic coupling here, so that's all fine. There's no frustration, there's no magnetic frustration involved here. And I can ask now the same question: is the total magnetization 0 by symmetry? And obviously, it is zero by symmetry. There is as much spin up and spin down in this system. Then the question is, what symmetry makes this magnetization zero? And you would say, well, this is like an antiferromagnet. So let's have a look at the symmetry, lattice translation times time reversal. I take this spin up and I translate it to the neighboring side and ask, do I get the same wave function back? But now I have to remember that actually, if I look at this spin up, it has interactions along this diagonal. And if I move it to the next, to the neighboring side, it will be on a side which has also diagonal interactions, but along the different direction, right? So you can prove this much more formally than I say now, but the wave function is invariant for translation by the lattice spacing, then doing time reversal, and then doing a rotation. And this rotation you need because of these diagonal interactions that are there, and the diagonal interactions on one for the spin ups, let's say, is 90-degree rotated from the diagonal interactions for the spin down. And one easy way to see this symmetry is go to the extreme checkerboard altermagnet, where I have only these green, only these diagonal interactions. Because if I have only these interactions, actually I can split the system into two independent systems. It's just I have one-dimensional lines of spin up interacting along this direction and one-dimensional lines of spin down in the other direction. And I know, for instance, that magnons, magnetic excitations, will propagate for the spin ups. They will propagate in one diagonal direction, and for the spin downs, they can also propagate, but if they propagate in the other direction. So this makes clear that for the system that is this composed of both the spin up and the spin down sublattices, I need a rotation to map the one wave function into the other. Okay. So now we get to what is an altermagnet. The material needs to have collinear magnetic order. If there is non-collinear order, more complicated things than just spin downs, up and downs that are parallel or anti-parallel, it's more, well, you can still, actually we are writing a paper also saying, explaining how you can make altermagnets in that situation, but it's a more complicated situation. Simple situation, collinear magnetic order. The magnetization needs to vanish by symmetry, as it does for an antiferromagnet. And one way to see it here, why this is an altermagnet, is actually that the magnetic ordering does not enlarge the unit cell. If I look at this system here, I already know that I have a unit cell that contains two sides, because one side has interactions, again, along this diagonal, and then the other side, the interactions are along the rotated diagonal. So the basis of this lattice contains two sides. And on that basis of two sides, antiferromagnetic ordering takes place. So what does it now mean for the itinerant picture? If I have a band system, actually, if I have a band system now, the bands will be split again by the exchange interaction. So I get spin split bands on the order of the exchange interaction, for instance, for a system like chromium and timonite. And the reason is that if I want to map, if I look at momentum and I do I look at the symmetry of a translation and time reversal and rotation, then I rotate momentum. If I start with momentum kx, I rotate momentum to ky. So this symmetry here does not leave momentum invariant. Actually, it rotates the momenta by 90 degrees in the checkerboard example. So if I have a band, if I go along the kx direction, I can have a spin up band. And if I rotate by 90 degrees, I find back this same energy and momentum. I find back a spin down band. And having this symmetry in the system makes clear that always there is a zero magnetization, because for any spin down band, there is also a equivalent spin up band, but just rotated by 90 degrees in the Brillouin zone. Yeah. So now I have so the very simple idea of, so I say fast and loose approach to ultramagnets is that you have collinear magnetic order, magnetization vanishing by symmetry. Magnetic ordering does not enlarge the crystallographic unit cell. This is sloppy talking, but just to give you the pedagogical idea, which means that the vanishing magnetization is guaranteed by a symmetry, a symmetry other than translation or inversion. Yeah, the vanishing symmetry in the example I showed involves rotation. The bands are generally spin split, which is very different from a normal antiferromagnet, because the spin splitting does not require spin orbit coupling. It is on the scale of the local exchange field, much larger in general than the spin orbit coupling. So what I talked about now in this first 15 minutes is not something that I invented, or the people that I mentioned in the beginning. Some of them actually. Sinova was very active in establishing this field. The first paper reporting momentum-dependent spin splitting by collinear antiferromagnetic ordering, which we now call ultramagnetism, was in 2019 of this Japanese group. I mentioned the group of Lieber-Schmeikal, Sinova, Jungwirth, and there's also the group around Alex Zunger that explored these ideas of having a spin split antiferromagnet as the first in the field. I take this now from
Jeroen, maybe we can stop for a moment for questions. If at least I'm feeling that I have a question. Maybe someone else.
Please.
Could you? I didn't understand this idea actually of rotation. What about spin? It rotates 90 degrees. It makes them horizontal from vertical. How to
spin,
be?
Spin is not rotating. So so the rotation does not affect spin. It only affects the lattice wave part of the wave function.
How it can be, or but okay.
Well, you define it like that, so that okay. So then we have to go a bit more in the symmetries. So I could also, okay, what I define as a symmetry is a rotation of the wave function around a lattice point, and in that rotation, I do not rotate the spin. As a mathematical object, I can define this.
Okay, okay. Maybe I probably don't understand, but also I wanted to ask you. You say it does not double the unit cell, comparing to antiferromagnet or comparing to original unit cell without spins.
Comparing to original unit cell without spins, exactly.
Original unit cell around spin. Okay. And but when you showed this electronic structure, which is degenerate for antiferromagnet, this means already for doubled unit cell, not for original unit cell, probably, yes?
Right. So for our normal antiferromagnet, you double the unit cell. Yeah.
And therefore you have degenerate states.
And each band is twofold degenerate.
Okay, thank you.
Okay.
Maybe more questions at this introductory part? Okay, then please proceed. Thank you.
Please go ahead. You have questions also later. It's very important to establish this. So now I will get to some examples and some consequences of this ultramagnetism. So, and one of the consequences is on the Fermi level, if you have a metallic ferromagnet or antiferromagnet or ultramagnet. So let's look at the Fermi surface or a sketch, the idea of a Fermi surface. How do Fermi surfaces look in a ferromagnet? Again, if a two-dimensional system with a majority spin, a minority spin, the band structures are shifted with, or the bands are split with each other. So you have a Fermi surface for the majority, in this case the up spins, and you have a Fermi surface for the minority spins, which are here. Now you see immediately that's a ferromagnet because there are more, the Fermi surface of the up spins is larger, so there are more up spins than there are down spins in this case. So the Fermi surface of an antiferromagnet, what will it look like? Well, the bands are twofold degenerate, so I will have a Fermi surface that's also spin degenerate. It's obvious. But now I have this ultramagnet. If I go from one sublattice again to the other sublattice, it requires a rotation. And here you can see that it's a lattice rotation. It could be some octahedra around the central atom that are elongated. And on one sublattice, they are elongated along the y-axis, and on the other sublattice, so that is the crystallographic sublattice, the elongation is along the other direction. In this ultramagnet, now, because of the spin splitting, also my Fermi surface will be spin split. So I have a Fermi surface for the down electrons and a Fermi surface for the up electrons, but because of this 90-degree rotation symmetry, they will be the same and rotated. So the volume they contain is the same, making again the system a fully compensated, symmetry enforced, fully compensated antiferromagnet. And now you see that this ultramagnet is already a bit different from this standard ferro and antiferromagnet that we know. And you can think about the property that could be interesting, which is the generation of spin polarized currents. So now imagine you start moving, you put an electrical field and start moving electrons or pushing electrons along this x-axis. It's clear if you do that, you will affect the up electrons, the blue bands, different from the red bands. So if you start pushing current here, in general, the up electrons and the down electrons will react differently to it. So you will get a spin, let's say an up polarized current if you apply the electrical field along the x-axis. But interestingly, if you would apply the same field along the y-axis, now you would get a down spin polarized current. So you have this fourfold symmetry in the spin currents that you generate, at least in theory. Now I come to...
And here, sorry, this band crossing here, they generate in theory, or it could be some hybridization in principle?
Good question. Yeah, so the question, the answer to the question is depends if you, in theory, consider spin-orbit coupling or not. So in this pictures, we did not think about spin-orbit coupling. And that decouples the spin-up and the spin-down sectors. And that means that I will have these crossings there. There will be exact crossings. If I have spin-orbit coupling, then what will happen is that let's say, spin-up and spin-down can hybridize by the spin-orbit coupling parameter. And that is especially important if there's a crossing, of course. And then this crossing will be, as you suggest already by asking the question, then this crossing will become an anti-crossing. So you will get a small splitting here, which means that you start with a spin down Fermi surface, it stays spin down, and then it starts rotating if you get close to this crossing point, and then here you continue on the spin up surface. And depending on the size of the spin-orbit coupling, that determines how large the region around this crossing point is where the rotation of the spin takes place, let's say. So the idea is of this ultramagnet, I can also introduce the spin-orbit coupling. It will introduce some new effects, but it will not affect, for instance, the physics that I talked about. It will change this splittings here, which is interesting, but not in a major way affect these spin polarized currents being present. So what I will do is, in the last 6 minutes, maybe only talk about some materials where this is relevant. So ruthenium dioxide is an example that I've shown before. It has this 2 rutheniums in the unit cell, and there's this structural rotation present, and the antiferromagnetic ordering, in this case, indeed does not break the lattice translation symmetry. Another one is chromium antimonide. It's a more complicated system. It's triangles of antimony atoms separated by triangles of chromium. And because of the stacking of these triangles, you get the same kind of altermagnetic situation, which is not so easy to see here. I take it now from our paper, where you can calculate the spin splitting, and you see here, if you go from gamma to X, then there's some, let's say, spin up band separated from the spin down. And if you go from 90 degree rotated from gamma to Y, it's the other way around. Yeah, you see, this is typical for an altermagnet. Chromium antimonide, the chromium form the layers of chromium are in the same direction. So in this case, you have a chromium layer up, then there's antimony in between, and then the next chromium layer is down, and there's the stacking of these layers. And that the lattice requires a rotation you can see from looking at the antimony here. If you look at this antimony here, it has 3 legs down and 3 legs up. That's the same as the antimony down here, but they are rotated. These objects are rotated with respect to each other by 30 degrees. Yeah. So to go from one antimony to another here, you will have also, it involves a rotation. And actually the same is true for the chromium. And this symmetry, which is not completely obvious from these pictures, makes this system an altermagnet and leads to a spin splitting. And this is for a calculation from our paper. And you see that in these bands, they are, if you're at a high symmetry point, where if you do a rotation from kx to ky, for instance, you map on yourself, okay, then these bands are not split. Yeah. So here in this case, at P1 and at gamma, the bands are not split, but in between they are split. And you see the splitting is quite large. It's about, could be even 1 eV for chromium antimonide. I'll just show you one result from our colleagues from Sweden with whom we worked, which is ARPES, because ARPES is in QMatS an important technique. They did ARPES on chromium antimonide. This is too much data. I'll just show you one cut at a certain energy, at a certain kz, where you see where they measure these bands are split by 0.8 electron volt. And that compares well with calculations, with the DFT calculations. So that is the first time that in chromium antimonide, that is a first measurement of the spin splitting in chromium antimonide. The last 2 minutes, you can ask how abundant are spin split antiferromagnets. We did a calculation considering 2,000 published commensurate structures from this MAC database, and you can see that well, a bunch are too symmetric to be altermagnets. Some are non-collinear, which also doesn't count. Some are not antiferromagnet, at least not in our calculations. And then we are left with 60 materials that are collinear antiferromagnets with spin split bands, at least to our calculations with the FPLO software. So these are now materials. And what we plotted here on the red, blue, and black are curves that are quantifiers for the spin splitting. Materials that you see is manganese fluoride, for instance, nickel fluoride, which are systems with the rutile structure. Cobalt difluoride also has a rutile structure. These are the two different measures of the spin splitting that we defined. And now if you look, for instance, at, let's say, cobalt difluoride, you see that by all measures that we defined, it has a large spin splitting. So what did we learn from this calculations? That there is a chemical trend, that the strongly ionic materials have largest spin splittings, which is probably not so amazing because they also have the largest exchange splittings. There are only few in this database. There are only 3, actually. 3 out of 60 altermagnets that are metallic, which is chromium antimonide, ruthenium dioxide, and this chromium niobium sulfide. We found some interesting ones, which have spin split bands that are very flat. If you have flat bands, this iron sulfide is one. If you have this very flat bands, that likely means that there is some instability in the system. So that would be something to look at with a bit more detail. Many of these systems have been considered in the 1960s, 70s, 80s. So, you know, at the time that people were just not looking at them as altermagnets, but just as a new material. So I think many of these materials are worth revisiting. I will not talk about the Hall and anomalous Hall effect, which I really like, however. We have a very nice paper out there. I'll just go to the conclusions now. So the conclusion is we have a substantial number of altermagnetic materials, at least 60. Metallic altermagnets are scarce, but interesting because they have these spin currents you can get there. Ionic altermagnets tend to have large spin splittings. Altermagnets have been predicted to have interesting properties in spin charge transport. I mentioned. I did not mention spin heat transport, which is also something we're working on. Piezomagnetism, anomalous Hall conductivity. We're also working on that. Actually, you have shown in the data in the RPEX data that actually chromium antimonide is a Weil semi-metal. So not only it's an altermagnet, it is a Weil semi-metal. It also has so it is topological. It has topological Fermi arcs. It is very rich and interesting. It has interesting magnetic domain wall structures. It's interesting if you put them on if you induce curvature, they have new magneto-optical properties, and there's much more. So that's what I wanted to talk about today. And please, more questions.
Thank you, Jeroen. I see there's, first I just wanted a short question. What about HTC cuprates? They are boring, yeah? They are not alter magnets.
Yeah, they're non-magnetic, right? So lanthanum to copper.
They are all antiferromagnets.
So I mean, the mod insulating ones are not superconducting, right?
Yeah, not super.
But here you look at the mother compounds or of cuprates, right? So I mentioned lanthanum to copper 04. Here you see also probably one you recognize, this yttrium 2 copper 205. There's this copper phosphide. Here's a copper vanadium compound. This is this is already the ruthenium. So there are a bunch of cuprates that are altermagnets that have spin splittings, but look at well, depending on which measure you take, those spin splittings tend to be small. So for our measures, around 20, let's say, where if you go to the best ones, you have a factor of 5 more. But yes, some of those mother compounds of the high-TC superconducting cuprates, they are altermagnetic. And it's a very good thing to do, I think, is to look at them, at those materials, which we might even have crystals of available, and look at them with the eye of the altermagnet, the new eye with the altermagnetism. Yeah.
But iron-based superconductors are not them.
No, I didn't read
metals. Okay.
But it can also be because they are not in that database yet. right? We took the 2,000 materials from that database and did a high throughput for them.
Okay, I could read a question from the chat. It is, could you please name any applications of antimagnetics? About applications.
Okay, so it's a very good question, and the answer is not that they are obviously opening up a new range of applications. I think at the moment we are opening up a set of fundamental questions. So it's fundamental scientifically interest that drives us now. But my colleagues are arguing that in spintronics, where you need this spin charge conversion, so driving a charge current and introducing a spin magnetization is important. At least that property is a property in the of altermagnets, or at least of these D-wave altermagnets here. And the why is this interesting? Well, in the same altermagnet, you can generate a spin up current or a spin down current, which in the ferromagnet you will not be able to do. Because in the ferromagnet, any current you drive has the same spin. And in this kind of altermagnet situation, you don't have stray fields. You still have a fully compensated, also locally compensated antiferromagnet. Whereas in the ferromagnets, you have long-range stray fields, so that will always lead to some kind of deviation from ferromagnetism if in the real life. For instance, domain structures will be generated by that.
Okay, think about more questions. And I just staying on this picture probably. I wanted to ask this naive question maybe about actually magnetization, and because just staying from this real-time cartoon, yeah, or real space cartoon. I would expect that let's say effective magnetization from blue spins from blue sides are different is different effective than from red sides, just because different combination of spins and orbits. But if you make a direction of the spin diagonally, then it would be the same. Therefore, one would expect some magnetization anisotropy. Is it? But you said, as far as I understand, that this total magnetization is forbidden by symmetry. Is it correct? Yeah.
So that is correct. I said that, and that statement is also correct. As long as I do not consider spin-orbit coupling.
Okay.
So you could ask, for instance, I have an antiferromagnet here. Without spin-orbit coupling, it has a compensated magnetic moment, strictly zero magnetic moment, because of this equivalence of the sublattices. But if I have spin-orbit coupling, I know I can induce Dzierzynski-Muraya interaction, which is normally something that happens for many antiferromagnets. Is it allowed by spin-orbit coupling that the DM interaction is allowed? DM weak ferromagnetism by Dzierzynski-Muraya interactions is allowed, and that then, and in general, the answer is yes. In most altermagnets, the answer is yes. Where it of course depends, like you suggest, on the direction of the ordering. Actually, if in this case, but now if the spins would be pointing out of the plane, in and out of the plane, there would be no DM. But if the spins would be in the plane, there would be some DM that would actually get a net counting and a net ferromagnetic moment. But that's then, say, much weaker and spin orbit introduced.
Okay.
Much weaker. Yes.
Okay, understand. Thank you. More questions? I switch to Tom, back to you. Okay, I see no more questions. It's new material really for us, and that was actually the first mentioning when I saw you for me. Thank you, Jeroen, very much, and for your nice talk with so nice introduction. And for I see the question from Alexei also. Please, Alexei.
I cannot understand. You said that spin, first of all, spin is not rotation, but the first question, if spin is not rotation, but what about mechanical angular momentum? And the second question about this is alter magnet scheme. You said up spin, down, up spin, down spin, but I see that direction of blue figure and red figure rotates one from other on 90 degrees.
Mhm.
What does this mean? Is this substance has zero compensated magnetic momentum, or maybe some vector summarized magnetic momentum. I mean,
you mean if it's a ferry magnet, maybe?
Not. I'm asking about alter magnets. About this.
So,
about this slide, which you show now. I don't understand why spin up and spin down, but blue figure right and up figure up. And what does this mean physically? And
yeah. So what these authors intended to convey here. So by this shape here is the real space distribution of the spin density, if you want. Yeah. So the spin is pointing up, but the spin density around the atom here is not spherical. And the same way, actually the spin density here is elongated. Yeah. So you can, and this shape of the spin density is rotated from one to the other. But the total, say, spin in the red and the blue is the same. And the direction of the spin between the red and the blue is opposite. Another way of thinking about this is if I look at this atom here, which is on the ligand, which is an oxygen in ruthenium dioxide, that would be an oxygen here. This oxygen is actually closer to the spin down than it is to the spin up. So you can expect this oxygen also to have a magnetization. And this magnetization of these two oxygens will be up, and the magnetization of those two oxygens will be down. And the same here. Those two oxygens will be down, these two oxygens will be up. So that makes it clear that if I go from one sublattice to the other sublattice, here the elongated ones are red. Yeah, here this one has more red spin. And now I rotate, then this guy I rotate here, it gets more blue, it gets more upspin. Yeah. So another way of looking at it is that the altermagnetic, in this altermagnet at least, you get a magnetization of the rutheniums, and this magnetization of the rutheniums induces a magnetization on the oxygens, and these oxygens are rotated with respect to each other if I go from one lattice sublattice to the other sublattice. This is the same reason I get the spin splitting. And your question about so I did not maybe emphasize well all these considerations so far of this consideration here is without spin orbit coupling. So this altermagnetism you can talk about, or it makes a lot of sense to talk about it as long or when the spin direction is not coupled to the lattice direction. The spins have their own space and the lattice have another space. So here in this example, the spins are rotationally invariant.
Okay, thank you, Jeroen, for answering. I think it's anyway, it's impossible to understand everything just from in
also a question about previous slide. There was a slide with two graphics with red and blue functions with asymmetric potential. No. Oh, this one. And the question is, I see that an dependency of energy on wave vector is asymmetric for red and for blue, and the question is what observed phenomena do we see with this description of this energy dependency.
For example, spin polarized ARPAs, you can see this.
Yes. And I note that this is Kx, this is Ky. So it's not Kx and minus Kx. So it's not anharmonic if you want to think about that. It is something different. So at Kx, you have a different wave vector where you cut the Fermi level as for Ky. So this picture implies directly this picture. Yeah. And this picture implies directly this spin currents. And this picture indeed also implies that you would be able to see that in ARPAs. And in spin polarized ARPAs, you would find a spin polarization of those bands that are corresponding to those spin projections that are calculated.
Okay, thank you. We should thank you for presentation. Thank you for questions. We should move on. We're a bit late this time. So the last speaker for today's session, Sergei Borisenko, who is known ARPAS expert, but now he is also inventor of a new spectrometer, and actually what he will speak about, I will see. Please, Sergei.
Hello, everybody. Thank you, Alexander. It is a great pleasure always to speak to such an audience. Since it is a school, I will start with a little bit of simple introduction to angular resolved photon emission spectroscopy. And this is very short, and I think it's very sort of very easy. And this comes from the analogy between the electrons in the solid and the fish in a, let's say, a lake. So in order to catch more fish, it would be good to know in which direction and how fast and how many fishes are swimming at a given moment. So this is kind of a fisherman's guide, would be good to know if you're going to fish to a lake. So if you have this kind of a map, if you have this kind of knowledge, it is always very nice to have. So this is actually the questions which we are trying to answer using the angular resolved photon emission spectroscopy. And in order to for fish to get out of the water, we use in this case the light, and I found the pictures which actually show that you can indeed, actually not only pictures, there are ways how to catch fish using the light. So I learned it, and it's indeed the case. So this is a kind of analogy which we are using to extract electrons from the solid. Another thing is that you can use that analogy with a fish which can escape from the water. This is our electrons, and there is, I learned to my big surprise that there is a flying fish actually. And basically, this is exactly what we are doing in terms of catching electrons, because they are flying away from the solid at a very different directions. And our task is to detect and to understand in which direction and how many and how quickly they're moving. So not all electrons have enough energy to escape, of course. They could be scattered by phonons, for instance. But those which can escape, they can also come, some of them can also come back, and only the fastest of them, they can make it, and then they finally get detected. So this is exactly the detectors which we use to detect the electrons. And there are different types of the detector. There are those which are focused on the speed, and meaning that as soon as the fish leaves the water, you can immediately detect it, and then you are very confident in which direction it left. And if you wait until it loses the speed, then you can estimate its speed, and then you can calculate its speed. So this is exactly the result of our measurements. We call it ARPA's onion. This is the fisherman's guide. I find this analogy very illustrative, because here in this case, you could see this amount of information. This is four-dimensional data set where you see if you cut the onion horizontally, you will get the distribution as a function of direction and direction. You need two variables to have it to denote the direction, to define the direction in space. And you can reserve another direction for the speed. So if you cut it vertically, you will get another way of representing the data, meaning that this would be distribution of electrons as a function of speed and direction. So in such a way, with this method, we get possibility to answer our main question: how many electrons are flying in which direction and with which speed. These are the detectors which we use, and ARPAS has been already introduced by Bernd, and our detector has been introduced. I briefly mentioned these two types. As I said, there are analyzers, they're called electron energy analyzers, which are concentrated on getting the distribution as a function of direction and speed at once. This is a unit of information. And in this case, this is the so-called hemispherical analyzer. In the unit of information at a given moment of time, meaning at your screen, you get the distribution of electrons as a function of speed and direction. And what we have done is we decided to catch our electrons earlier. In this case, electrons have to go through the lens, and then they're sorted by energy by hemispherical analyzer. In our case, we do it at a very short distance, very close to the emission of the electrons. And in this case, we are concentrated on the direction. So basically, we detect our electrons very close to the sample, and this gives us the distribution as a function of direction here and here. This is technology which is now patented in Germany, USA, Japan, China, and the patent is pending in European Union. It turned out it's a very simple thing, but it turned out to be not known earlier. And for the comparison, the electrons here fly around 1 meter in order to be detected. Detectors are the same kind. This is multi-channel plate in this case and in this case. And in this case, the electron fly only 12 centimeters. So nearly an order of magnitude. The very instructive, very helpful thing to have is to have both in the chamber. And I show you what you see on the screen in the same room. You see the same ambient situation. We have, once we run the hemispherical analyzer, we have distribution on the screen, angle versus energy. And when running FESUMA, which we call FESUMA, it means Fermi Surface Mapper, then you see the Fermi surface at once at the same laboratory, at the same chamber from the same sample, basically. So this having both allows you immediately to see, to cut the onion horizontally and vertically. These are the examples of the ARPIS onions for real materials. This is the bismuth tellurium, very famous Drosophila of ARPIS experiment. You could find a lot of data on the internet and in the literature. And this is kind of testing crystal also for us, although there is interesting physics inside. So we measured it. And here you see that you can get the horizontal cuts, then you get the momentum cuts, and then you can get the vertical cuts, which show the distribution as a function of energy and momentum. Good. So with this, with these possibilities, we of course trying to address very interesting physical questions, and I switch to the main topic of my talk. This is platinum bismuth 2. It is extremely interesting material, as it happens very often nowadays. The material has been known before, and there are many different types of this material. What I will be talking about is the trigonal version of this material. This is a particular crystal structure, and interesting is that even we studied the similar material earlier, actually the same, but we didn't find everything what we found now. The band structure of platinum bismuth 2 of trigonal modification is pretty difficult. So we have 5 bands, even according to different calculations, you can get even 6 band crossing the Fermi level. So the Fermi surface at the first glance is very complicated, but if one has a closer look, then there are quasi two-dimensional objects. Maybe if one looks at that, this Fermi surface would probably could see some kind of layered structure, and this probably explains why the material is cleavable. Because in order to make ARPIS experiment, one has to cleave the crystal if one of the methods to prepare the atomically clean surface. And this is probably the explanation why it is cleavable, although it is very three-dimensional according to number of bands and the topology of the Fermi surface. In any case, this has been known earlier, and why the renewed interest is because our colleagues, Jeroen and his colleagues from the Theory Institute in IFW, after my experimental colleagues from Institute for Solid State Research saw very interesting tunneling spectra and also transport properties. So this was a joint effort of IFW researchers, and they found out in particular that this is a wild semi-metal. As you heard, most of the Dirac wild semi-metals were known earlier, but it was the particular crossing of the bands, non-degenerate crossings of the band in a single point has not been noticed earlier. But now it is a very interesting subject to study, and it turned out this platinum bismuth 2 had 12 symmetry-related wild nodes, and they are located slightly above the Fermi level. And of course, if the wild semi-metal, if the band structure is of the type of the wild semi-metal, then one expects interesting properties also at the surface. And these are the results of my colleagues who did scanning tunneling spectroscopy. Here you see that material cleaves gives a very nice surface. This is very important also for our measurements. And what they saw is that actually there is a type A, type B surface, which is not surprising because the material is non-centrosymmetric. And the unique property of this material is that it turned out when we cleave the sample, you can always mark the particular sample surface A, and if you cleave it again and again, you will also get the surface A. This is quite a unique situation because most of the non-centrosymmetric materials, they grow with the stacking folds, and depending on where you are at the surface, one could really see one type of determination or the other type of determination. So in this case, this is a unique and then very helpful for the experiment material, because if you cleave it, if you open it in vacuum, then it will always be either one surface or the other surface. And in order, for instance, in order to study both, we cleave the crystal in air and flip another part and glue them together. So one could select which surface A or B to study. These are the calculations, and as I said, there are interesting properties expected in case of wild semimetals. In particular, at the surface of a wild semimetal, between the projections of the wild points I mentioned earlier, this is the place in the momentum space where they where the bands cross and in a single point. So when these points are projected to the surface, between them there are states which are called Fermi arcs, and these surface states are rather unique because they are non-degenerate and they are different at different surfaces. This is termination A, termination B. They connect the wild points. Apparently, they are connected like to the one side, but if you have a closer look, this arc has a complicated shape. It goes like this. And of course, the question, yes, we studied this material earlier, but how about the arcs? We want to see the arcs since they're predicted and they should be also visible in angular resolved photoemission spectroscopy. And we started with a brute force approach, like at the synchrotron, you go and do very many different photon energy in order to understand the three-dimensional electronic structure. And here you see the Fermi surface maps taken at very different energies, starting from 15 to 43. This gives us an idea where we are in terms of Kz. I was talking about during the simple introduction about the two dimensions of momentum, but there is a third dimension of momentum. There is another nice analogy with this, but not for today. And to make it short, there is photon energy which can probe the Kz. So we have another direction of momentum, and this direction can be probed by the photon energy. So by comparing with the calculations and having these many Fermi surface maps, we could figure out at which photon energy we cut the Fermi surface at which Kz. For instance, if you find a certain degree of similarity between the experiment and calculations, and in this particular case, you see how this triangular shape, so you have this point and you have the side, and it is flipped in this case, so you could identify approximately where you are in the Kz. I'm saying approximately because Kz resolution of ARPAS experiment is not as great as Kx, Ky, but in this case, one is still able to do that. So this means we have access to all three momentum components and energy. So fully four-dimensional information about the electronic structure of this material. There is a certain degrees of similarity. We found the gamma point, the A point, high symmetry point. This is how the momentum energy cut look like they are really similar. There are always some deviations from the band structure calculated, and the experiment, we got used to them, but this is very helpful because we can identify these bands anyway, and we know which feature is responsible for which calculated feature. So this is experiment, this is theory, this is experiment, this is theory. I noticed earlier that the wild points are situated above the formula. And in order to answer this question, we went to the central laser facility where there is a unique possibility, well, not unique, but very nice possibility to do pump probe experiments with different energy, with different harmonics. I think to this extent, this is a unique possibility. And there we did the experiment with the pump probe experiment pump probe, meaning that usually ARPAS sees only states below the Fermi level. And in this case, with the aid of additional laser, one can pump the electrons to the unoccupied states, and the electrons from these unoccupied states can be picked up, and one could have a glance into the unoccupied electronic structure. And indeed, well, not exactly, but very close to the predicted theoretical value of 45 millielectron volts, we found that these wild points is there. There are very nice also data analysis, including machine learning in these two preprints, which show also that the dynamics in these near the wild cones is pretty similar to the graphene, where the electrons cannot decay very fast when there is no phase space. So exactly in the vicinity of the wild points, this happens, and these relaxation curves are showing this. Again, in order to find out where we are, we used FESUMA there, and we saw the Fermi surface, which was on the screen. We know what the orientation of the sample, we know the geometry, and then we go with the hemispherical analyzer and do also another cut. They also have two analyzers in one chamber. Okay, so wild points are there. How about the Fermi arcs? And this is our first attempt. We used the laser in the lab. In ARPAS, one can use very different light sources. I mentioned the synchrotron with the tunable photon energy. I mentioned the central laser facility, where one excites with the higher harmonics of the laser. We have also the laser in our lab, and we have a couple of them. This one is 5.9 eV laser. This is our first attempt to see the arcs in platinum bismuth 2. And this first attempt actually showed that this is the map, the portion which we studied. And the arrows show the cuts through this momentum space. At the first glance, we were happy to see the bands. That was pretty good, because laser experiments are usually pretty complicated. In the case of three-dimensional material, this is the case. But the band structure was there. It was sort of similar to the predicted band structure. And this is how the typical energy distribution curve looks like. I showed you one could slice onion horizontally and vertically, but one can slice also the slices in order to get the lines, right? So this is the slice through the vertical slice of the onion, and it's called energy distribution curve. We saw the reasonably sharp peaks here at the Fermi level. But we didn't notice the arc. But then we started to investigate higher rotation angles in order to catch more electrons, not only those which were immediately seen, but also those which fly away at very different angles. And then we realized, and I show again the screenshots of just the photographs from the laboratory, because this feature which you see here energy is horizontal and direction is vertical. This is a hemispherical analyzer. This is this unit of information, vertical slice of the onion. And we saw this feature directly on the screen. First, we thought this may be an artifact, and then we had a closer look. This turned out to be exactly the feature caused by arcs. But we have never seen these kind of features in angle resolved photoemission spectra. And it turned out that nobody has seen such features, such sharp and strong features in angle resolve and in photoemission from solids, one could safely say that. So it turned out that these small portions of the map are arcs, which we first detect with that. We saw that they are very flat. They're sitting very close to the Fermi level. And again, exactly in the places where the theory predict them to be. So these are calculations along the cut, I think the vertical cut like this. And then you could see that experimentally and theoretically, they are located very close to the Fermi level. In order to give you an idea how sharp the peak is, I compare with a very decent EDC I showed you in the previous slide. That was from the bulk state, and this is the surface state which we observed. At that time, we thought that this is the record, as I said, in the record in the history of solid states, photoemission from the solid states, but I come back to this point later. So now we know that there are arcs, we know where to search them. We went again to the synchrotron and had a closer look. You need to have a very high resolution in order to record such data. That's why This time we concentrated on very low photon energies, because the lower the photon energy, the lower the kinetic energy. The lower the kinetic energy of the photoelectrons, the higher the resolution. And these are, I think these data are taken with, I think 12 electron volts. And here you start to see arcs, these small points, these small points here. It was tempting to say that this is arc, but this is not. This is this feature from the calculation. So the arcs are these small points here. Difficult to resolve at the synchrotron, but nevertheless, in the vertical slice of the onion, you can clearly see these two. This is horizontal slice, and this is vertical slice. Again, as the theory predicts, these features are there. So the arcs are situated at these positions, exactly where the theory predicts them. And even at higher photon energies, where the resolution is worse, one could still probably track, if you follow what I'm showing, then you could probably track still the arcs actually at all other photon energies which we see, which we studied. And this is important because when the photon energy changes, three-dimensional structure changes, because we cut at a different KZ. If we study surface states, they should not depend on the photon energy. Of course, the intensity could be a function of the photon energy, but generally they are not depending on photon energy. So this was a confirmation that these are surface states. Again, we did it at different energy and with the laser compared with the theory, so there was no doubt that this is exactly these states, and they're very well separated from the bulk. So you see how sharp these features in theory, and in the bulk there are no such features. This is exactly what is seen in the experiment. Of course, having studied the superconductors during the many years, we decided to look at the temperature dependence, because such big, unusually sharp peaks appeared in the superconductors. And if you see here that warming up the sample from 3 kelvins to 30 kelvins, you see that this flat dispersion turned out, this flatness and this coherence got lost. So this is a very typical sign of the superconductivity. We investigated it closer, and we found another typical sign of the superconductivity. This is zoomed in picture of the Fermi arc. You see the energy scale here is only 14 millielectron volts, and the cuts from the vertical slice of the onion are here. And you see the typical sign of the opening of the superconducting gap. We call it band bending. This is how it is predicted in BCS theory. Well, I'm not saying this is a BCS standard BCS gap, but there is this band bending, which is very, this is a very good signature of the opening of the superconducting gap. So we saw it at different samples, and that's why we concluded that this is actually the superconductivity. Again, our colleagues simulated the superconductivity on the arcs, considering via the Bogoliubov-Dujan formalism, and they added the superconductivity in this case to the arcs. And indeed, this was a very good qualitative agreement with the experiment. Even quantitatively, one could see that the bulk remains non-superconducting and the surface is superconducting. If we, so this is the kind of smoking gun experiment. You measure at low temperatures, you measure at higher temperature, and you see how the shift, how the energy distribution curve shifts. This indicates strongly that there is opening of superconducting gap. And this is in the colors red, white, blue. This is a different spectrum above TC and below TC. And you clearly see that nothing happens with the bulk, but only surface feature clearly shifts and the gap opens at the surface. So we did it in this case for several samples. We tracked the position of this peak as a function of temperature, and typically this kind of drop indicates of critical temperature. So in this case, we showed the data for 4 samples, and they are, this is the broadest transition is shown here. So this is how the superconducting gap opens. It's not big, it's a couple of millieV, but this indicates the opening of the superconducting gap. And from these plots, one could roughly estimate the critical temperature. So there were around 10 kelvins for one surface and around 7 kelvins for another surface. They were turned out to be slightly different. This is the value of the superconducting gap is in a remarkable agreement with the STM data. We have this data from our colleagues. they showed that the gap is inhomogeneous on the sample on the surface, but the average is 1.5 millielectron volts. This is exactly what I just showed. And there's a typical behavior with magnetic field, unambiguously showing that we deal with a surface superconductivity. This is also confirmed by other methods. As I said, the transport properties with the with the thin films are consistent with unusual superconductivity. And data from Oksana also showed that with approximately the same value of the superconducting gap of the order of a couple of millieV, and with the value of TC, this is a pretty good agreement with our data taken from exactly the same samples. So what does it mean? Why is this cool? Why is this important? Because in order to realize a topological superconductor, one needs to have a lot of components. The main research was along the let's find either known superconductors, let's find topological properties in them, or let's make the topological material superconducting. But this is not sufficient. One has to have a particular type of superconductivity in order to be so that it's not trivial. Not trivial superconductivity means, in analogy with non-trivial insulators, one has to have additional states which are required by symmetry. So in this case, these are long-thought Majorana fermions, Majorana zero modes, which are elusive until now. The number of experiments to detect them, apparently they were there, but then they're not. So in this particular case of wild semi-metal, we have these non-degenerate arcs in 2 dimensions already for free. So we have the arcs, and then if they become superconducting, this is a very strong suggestion that this could be a topological superconductivity. But just observation of the superconductivity on the arcs was not sufficient, because we were not sure whether this superconductivity is trivial or not. So then we made further steps. Again, we took samples and started to look at the arcs even with more precision. Again, we have 2 analyzers. This is with helium lamp. You have a general orientation, the Fermi surface at once. You can rotate this. These are Fermi arcs. Fermi arc is here. You can figure out at which angle you can catch them. Then you can use the laser in order to have them better resolved. This is another laser. And then if you know a lot about how to measure the Fermi arcs, you can get this kind of image. This is a very big breakthrough in comparison, even with our previous measurements. So these are very new data, and you see how nicely we can resolve the Fermi arcs. Then, as I said, at that time, we thought that was a record. So now I can tell you, this is the record. Actually, both in terms of energy distribution, the width of this peak is 1.7 millieV. This is in terms, it's not in terms of resolution, but in terms of the sharpness and strength of the peak, signal to noise ratio and its width. So this is 1.7, and also in momentum, this is 2.2 milli reciprocal angstroms. I always put 0.0 something, and our student now postdoc, she said, this is milli reciprocal angstrom. So now one could say about a milli reciprocal angstrom is 1,000 of a Brillouin zone. This is a very good precision. So this is how this dispersion looks like. Already this dispersion shows you that this is a very unusual feature, because usually photo emission data are pockets. If the shallow pockets, or then the dispersion goes there. And in this case, it's kind of lost from the other side. This is the signature of the Fermi arc, because arc is not complete Fermi surface, just a portion of the Fermi surface. Therefore, the underlying dispersion should cross it, and then from the other side should disappear. This is the data and the precision which is achievable. So, having this precision, of course, one asks the question, how about the superconducting gap as a function of momentum? And it turned out that the dependence is very interesting. And as we saw this, we immediately went to our theory colleagues, but the magic word node, somehow we didn't realize that. Then we heard from a theorist that indeed, so we have the superconducting gap, which is finite at the wings of the arc, and which is 0 in this direction. It means that Now we have the superconductivity, and this data just support this. So if you compare plus 90 degrees, minus degree, and 0 degree, so you can code the position of the arcs by these degrees. So you compare this point with these two, and you clearly see the effect. And then you see how the gap closes, and then you see how this is just supporting data for the paper. And this is reproducible, so you can measure the gap near the node in different samples. You can see that superconductivity is reproducible. So now we know that there is a node of the superconducting gap at the fermion. And this is already a very good, this has been shown for the top surface, for the bottom surface. Now the samples are oriented, so we can measure it more easily. Nevertheless, experiments still very difficult. And there is also very interesting temperature dependence, but this may be the next study will be devoted to that. But important thing that the superconductivity has now node. So as I said, we have a very unique object. We have we have a non-degenerate spin states localized in terms of energy, in terms of momentum, actually in terms of space too. So, and this is a very unique object, and it becomes superconducting, and it has nodal points on it. So we believe, and our theory colleagues believe, that this is the all necessary requisite for having the topological superconductivity out there. So there must be somewhere the Majorana fermions, and the Majorana fermions are usually detected in a single particle spectroscopy, if it's possible, as a single peak at a zero at a Fermi level, or as a tunneling people say, at a zero bias voltage. Maybe you heard about that. So we are hunting for peaks somewhere at a zero energy, and we, in this particular case, it is far away from the arc, but this is still pretty sharp peak. We can find them in some other places, so we hope that maybe this would be this Majorana fermions. So at this point, I would like to stop showing the data. I would like to thank all my colleagues. These are, first of all, the people from my group who did the measurements. You see that two persons have origin from Kyiv Academic University, crystal growers without which would be very difficult. There's CLF people, BESI people, theorists, more theorists, and our directors, Jeroen, you heard two talks of them. There's the Bernd is the driving force for platinum bismuth 2. He convinced me to measure it again, and so I'm very grateful to all of them. I'm grateful to you for the attention. Дякую. Україна переможе.
Thank you, Sergey, for a nice presentation. Please, if you have some questions, it's a good time to ask. Maybe while people thinking what to ask about termination. Actually, two different terminations. So could you see both of them on one cleave usually or not?
No, this is a point. This is an interesting thing. So you cleave it, and you always see surface 1. So the guys even mark the sample, like sample holders, surface A, surface B. So you can go to the synchrotron another time, another beam time, you cleave it, and it's surface A.
But in principle, it's maybe it's similar to different compounds. This is some, but stairs. Usually you have stairs, right? All right, but anyway, it's only one termination. Yeah, it's interesting.
We have terraces when we cleave. Terraces is not a problem. We have the edges, and this is where we are hunting. This is where the Majorana should be running around, right? So we want to catch them there. I can show also the data where with Fisuma, you can study many points. So the guys made 400 maps and found in which position the feature is more pronounced. And we now want to understand whether it's more pronounced where there are terraces or more terraces, trying to catch this. So terraces are there, but the surface is always the same. And this is in agreement with information that you get from tunneling people.
Interesting.
Yeah.
Okay. Please questions. Okay. Then people are tired probably, and everything is clear. Okay, thank you, Sergey, and I thank all the lecturers now for all presentations and for your support of our joint research. Probably I could I got question yesterday about day before yesterday, but nevertheless about possibilities of scholarships for master students, and actually we discussed it with ministry. They said that the most probable way, if we reduce or formulate this form, this scholarship in form of 3 months plus 3 months with some return back to Ukraine. And I think before we did it for 1 semester, yeah, but I think in principle it's possible to do it and to start with such a scholarship, and it will be more likely that we can proceed.
So let me just answer, because okay, I don't know whether Sylvia is still here. I think we can do it in 3+3. We will find a way trying to do that. Now, this 1 semester has an advantage because for the students we have also had the connection to the university, which makes life here more easier, because then the flat finding an apartment is easier, and they get some bonus when they use public transport. But okay, in any case, we will also manage to do it with 3+3 months. That's, I'm sure.
Yeah,
Sylvia, do you agree or not?
My microphone. I fully agree. I think we will find a way. It may be, so I think the most difficult point is actually accommodation.
Yeah.
But
yeah,
we will find some way of
sort
this out.
But Sylvia, students will inscribe at the TU Dresden, independent if they are here for the whole semester or just for 3 months or 4 months.
Yeah, I mean, the thing is, if they come for 3 months, then they need to inscribe twice for the semester and so on, this kind of details. But such short, very short visits, we need to check, because even it's maybe possible without passing through the uni. I don't know, because currently this was relevant before war and so on, because of visa and so on. But currently Ukrainians can come for 3 months without any visa.
Yeah, maybe this is still an advantage then.
Yeah, which may be an advantageous situation. The thing is, can we find affordable rooms
Okay, we will
for 3 months that do not belong to university? But I think we need to have a look, and in principle, why not?
So
better to have 3 months than nothing, I think.
We say, yes, we will find a way. And
yes.
That's the answer. And the other story is, okay, that's of course a typical boss statement, and poor Sylvia has to find a way. So, but okay, but I'm sure we will find a way.
Okay, I see Kirilla wanted to ask something.
Yeah, just want to mention, I posted link to chat. It's a new European program for funding master's programs, including photonics, quantum technologies, nanoelectronics, etc. It's 10 million euro per consortia of 3 universities and probably EDX and other stuff, and aim to train each consortium of 3 universities should train 150 students, I think, per year. And scholarships are also in the scope of this grant, so we could shape some maybe program between KAU, TU Dresden, and maybe some other Kyiv university like KNU or Kyiv-Mogila University or
so that's very interesting. So in principle, having already this connection between Kyiv and us, we should definitely try to check in more detail. We can either ask a second university from Ukraine, that would be very good. If you have another university, maybe Lviv or something like that, I don't know, Kharkiv, I don't know. We could also try, of course, to involve another partner here in Germany, or we can ask Prague, for example, which will make the story more difficult. But maybe we have a partner in Germany as well. So I think the suggestion is that we will have a close look on the call, maybe both of us, and check, and then also check for possible partners, because it's since it's master studies, it has to be university driven. But okay. On the other hand, I think okay, we have partners, we have a lot of friends, and maybe we can do something. Or we can even, in principle, we could even involve Genova or something like that, Italy. Maybe that's even stronger. So and they are also very open. So we have a good contact to them, and we can try. Italy is also attractive, you know. Okay, maybe that's the way.
Okay.
Yeah, it's because we shaped already master in photonics program with Alexander, based on the Institute of Physics, but not enough resource, and here is resource coming to push it forward, and for quantum technologies too.
Yeah, for photonics and quantum technology, or Würzburg, we can do it with. I say in Germany,
Yes.
it's straightforward to do with Würzburg, because we have this excellence cluster, which we mentioned, which is together with University of Würzburg, and their topological photonics is a part of a story, and I think that's easy to argue that we connect Ukraine with this strong excellence cluster in Germany. That's very straightforward to write, and there are a lot of things we can simply transfer. If we have to check whether we need another country, so if we need another country, then we can. Okay, we have partners in Toulouse or in Genova or in Salerno. So we have several ideas where we can do something. No, but I think that's a good idea. So, but okay, putting that to master means it has to be university, and this makes maybe a little bit more difficult, but we will see. We'll check.
Okay, thank you. Then we should finish our session today. I remind that tomorrow that will be another session starting from the morning, 11. In Kyiv.
But this will be in Ukrainian language.
Yeah,
I learned.
in Ukrainian language, right?
So I apologize. So I will not try. So that's no idea.
If you join, it's not a problem to switch in English. So yeah.
No, come on, it's okay. Do it in Ukrainian. Okay, good.
This was just the initial idea.
So in any case,
thank you very much.
Looking forward to the project. Let's go.
Thank you very much, Bernd and others. Thank you, Sergey, and all the speakers. Jeroen is left, I see. But it was a pleasure to see you, and very nice presentations. Thank you.
Bye-bye.
Bye-bye.
Bye-bye, and have fun tomorrow with the Ukrainian session.
Thanks.